Are you ready to be liberated from the tyranny of the lecture? Ah, come on. I know it's Friday afternoon. I mean, we need some more energy here. Are you ready to be liberated from the tyranny? Good. I'm here to give you a lecture about that. Well, there was some confusion about the instructions to get on. If you had time to create an instructor account, that's fine, because that gives you also 100 free student accounts, so that's nice. If you haven't yet gone through the instructions there, create a student account. That takes much less time, and you can use the free code demo, sign-up code, so you don't have to pull your credit card. Just type in demo when it asks for a code, and join the session 1, 2, 3, 4, 5, 6, 7, and then pick your seat from the seat map. If you're at a remote site, you can't pick your seat from the seat map, because the seat map is this auditorium, and you'll ending up sitting in the lap of somebody else, which will, create havoc with my little experiment later on. So if you're watching remotely online, do not pick your seat. Just say, I can't find my seat. Okay, well, we're here to talk about education. And in order to have a meaningful discussion about education, I thought I'd start with a little exercise where I make you reflect on your own education. So I want you all to pull a little piece of paper, or you can put it, if you have a device in front of you, you can use that. And I'm going to ask you to write down some very personal information, but you will not need to reveal it to anyone else. That's why I'm using paper and not your device. I want you to think of something you are really good at, something you're proud of, something you know you do well, and ideally something that has contributed to the success of your career. It could be interpreting medieval works of art. It could be solving partial differential equations. It could be identifying new exoplanets. It could be baking cakes, or photography, or public speaking. Again, as I said, ideally I'd like it to be connected to your career. So unless you're a baker, baking cakes will probably not be in there. In case you didn't write the instructions down how to get on, go to lcatalytics.com, create a student account using the free code demo. We'll need the system very shortly. And then join the session 1, 2, 3, 4, 5, 6, 7. And you'll be on. Okay. Usually when I ask this question, think of something you're good at in an academic environment, there's always somebody who raises his hand and say, only one thing? Yeah. Pick one thing, whatever it is that you feel really, you're proud of it. You know other people respect you for it. Who needs more time? Okay. You don't need to write down an essay. Just pick something, okay? Because once you've committed to this, I want you to reflect on the next question, which is the really hard question. How did you become good at whatever it is that you wrote down? Think about that for a moment. Where did you develop that skill or that knowledge that you picked? So I can see at once from the faces that, that's a little bit harder, right? Because when we're good at something, we tend to enjoy it. And when we enjoy it, we become unaware of how we learn. So in a few words, describe it, and please enter in your device those few words that describe how you became good at whatever it is that you wrote down. So I have done, while you take your time to write that down, I've done this little exercise all around the globe. It's really fascinating. I've done it all over Latin America, from Patagonia in Chile all the way to the north coast of Colombia. I've done it all across North America, from Mexico, from Central America actually, to Canada. I've done it all over Europe. I've done it all over Asia, China, Taiwan, Thailand, Malaysia, you name it. I've done it all across Africa, from South Africa to Cairo. And if you look at the answers that people provide to the second question, there are no cultural differences. There are no differences between the answers you get in China or in Chile, Patagonia. Yes, there are cultural differences between these people, but if they describe the way they learn, it's the same, which is probably not that surprising because we're all wired, our brains are wired to learn in the same fashion. And I'm pleased to report here that Vancouver, British Columbia, is no different from anywhere else. I'm going to show the results on your screen. It should appear right now, a word cloud. For those of you who don't have a device or haven't managed to log on yet, there it is. We learn by practicing. In fact, there are several spellings of the word practice that appear there. We learn by doing, and the other verbs that are there also have to do with self-directed learning and with things like motivation, discipline, reflection, and so on. So we see that no matter where you ask around the world, I mean, you see it for here, but I've seen it all around the world, people report by a big margin because you see that the word practice is significantly larger. The size of the word basically reflects the frequency at which it has been entered. That people learn by practicing. And how do we teach? This is how we teach, by lecturing. This is actually a picture of me teaching my first course at Harvard when I was an assistant professor. It's a very old picture. It's taken BC, before computers. See, I'm using an overhead projector there. Now, when I started teaching at Harvard, I never asked myself how I was going to teach, which is kind of odd, right? Because when you do something new in your career, that's the first question you should ask yourself. Unconsciously, the answer to that question was completely clear. I was going to do to my students what my professors had done to me. I think we all tend to do that, right? To project our own experiences onto the world around us. Something, you know, small children already start doing. Dan Gilbert, I recently had a discussion with him, pointed out to me, he showed me a picture of a little child that did this. And he asked me, what is that child doing? Do you know when you see a picture of a, let's say, 1-year-old do this, what he or she is doing? Hiding, exactly. Hiding, because the idea is if I can't see you, you can't see me. A show of egocentrism, but it turns out that we all possess that same type of egocentrism until very late. I mean, I was projecting my own experiences onto my student, thinking I had learned physics pretty much in a situation like that, therefore my students were going to learn physics that way. So we see here right off the bat that there's something strange, right? The things that are really important in your, something that was really important in your career, you learned it by practicing, by doing, yet all around the globe, our learning spaces are designed very much like this one here, and we teach basically by lecturing. So I'm going to spend a little bit of time, I spent quite a bit of time this morning for a different group deconstructing the lecture. I'll spend a little bit more time deconstructing the lecture here, for those of you who were not at my presentation this morning. Then I'll talk about an approach I developed to teaching that I think is much more effective and that can actually be used even in a learning space that is as poorly designed as this one or that one. Where does this architecture date back to? When was it first invented? By the Greek, exactly, the amphitheater. Except that the Greek designed it not for learning or teaching, they designed it for theater, performances, right? To focus the attention of many on a few. If you actually look at an illustration of the school of Athens, you see something very different. You see people walking around in pairs and talking and discussing. But somewhere in the Renaissance or late Middle Ages, we adopted this architecture as our architecture for teaching, and I think the lecture has continued to be entrenched as the dominant vehicle for education for many, many hundreds of years. And in essence, you know, we're still stuck in the Middle Ages in education. And in the last part, I want to talk about peer instruction 2.0. We'll basically have fun using learning catalytics to see how we can take this approach of the interaction between peers in the classroom to a new level. So let's start by talking briefly about the lecture. The exciting stuff will come at the end. And ask ourselves the question, what is it that happens in a lecture? If you look at this picture of me teaching, what is it exactly that is happening? I want you to describe the process on the screen behind me. And ideally, I want you to use a verb. And the two verbs I do not want to hear are teaching and learning. So you have to find another way of describing it. Go ahead, blurt it out. Listening. Writing. Copying. Ignoring or boring? Sleeping? Who said sleeping there? I mean, these are my students. But now that you mention sleeping, it never fails. You know, whenever I'm in an audience of academics, there's always somebody who says sleeping. So I'm prepared for that. This is a quote by the French writer Albert Camus, who said, "Some people talk in their sleep. Lecturers talk while other people are sleeping." And it turns out that that quote is actually very close, very close to the truth. I'll show you some data in just a second. I need a different type of description here. So we've heard listening, ignoring, sleeping, writing, talking, and so on. So I need some more description. Explaining. Now we're talking actually about, this is the first verb that pertains to me, right? Most of what we heard so far pertain to the students, but I'm there too. Telling. Can we find something that describes the whole, not just what I'm doing or what the students are doing? Banking method. Depositing. I had a trouble visualizing what you meant by banking method, but I like the depositing, yes. I would say, but what is being deposited, by the way? Knowledge, but how would you information? I know how I can transfer information, but I don't know how I can transfer knowledge. Right? So I think the adequate description would be lectures focus on the transfer of information. And you know what? My students have pointed that out very early in my career, but I had ignored it. You see, I didn't ask myself, what am I going to teach when I started? What do you think the question was that did come up in my mind? Sorry, I must be tired. I didn't ask myself how, I did ask myself what. So I went to a colleague who had taught the course before and asked him that question, and he said, oh, in this course we've used Halliday and Resnick. I've been educated in Europe, and in Europe you would never get into your mind to buy a textbook for an introductory course, right? After all, the professor was going to present the content of the book, so why spend the money on the book? But I was told that in the US, the students all buy the books for the introductory courses. So I went to the bookstore at Harvard Square, and I said, make sure that you have 150 copies of Halliday and Resnick in stock for September 15th, because that was the book that had been used so far. So as I walked back from the bookstore to my office, I thought, wait a minute. If the students have the book and I have the same book, then what do I do in the classroom? So I went back to the colleague whose advice I'd asked about the choice of book. And I asked him that question, and he said, oh, don't worry. There are lots of different physics textbooks. And he showed me his shelf full of different physics textbooks. I looked around, and very quickly I found the perfect book for myself. It was perfect for two reasons. One, it had a different approach from Halliday and Resnick, so at least I was not regurgitating the content of the book that the students had bought. But that was not the important reason. The important reason was the book was out of print. They couldn't get a copy of it. So for each class, I spent countless hours preparing lecture notes, which in class I would either project on the overhead projector or I would write them on the board behind me. Now, because the notes were different from the textbook, I decided to hand out copies of the notes to my students. So as they walked, the classroom was very similar to this one. It had the exit at the back, at the back of the hall. So as they walked out at the end of the classroom, they could pick up a copy of my lecture notes. Now, why do you think I handed them out at the end of class and not at the beginning of class? Why? So they would stay or not listen. But you know, isn't that already admitting that there's a problem? I mean, why force the students to get the information out of my mouth if they could have gotten it out of my notes? Never came up. But this is what happened. What happened was that at the end of that first year, I got really high ratings. I taught this course, which was an introductory physics course for pre-medical students. These were not students who wanted to learn physics. In fact, most of them hated physics already before setting foot into my classroom. And most of my colleagues would come close to committing suicide at the end of the semester when they saw their evaluations, but not so for me. I got high evaluations. So what happens when you get evaluations? Well, you get punished. They ask you to teach the course again. So the following year, they asked me to teach that same course again. And I said to myself, you know, rather than issuing these notes lecture by lecture, I'm going to, before the semester starts, take all the notes for the entire semester, collect them, send them out for duplication, and on day one, each and every student receives a complete packet of notes for the entire semester. You know what the unexpected result was? The unexpected result was that about half a dozen students wrote on their evaluation questionnaire, Professor Mazur lectures straight from his lecture notes. Hello, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I handed out? I mean, I was livid. These ungrateful students. But you know, the students had a point. I was focusing on the transfer of information. And in fact, if they had read the book, they would have seen that the book was not that different from the lecture notes I gave to them. Now, given that this approach that you see behind me is one that is used all over the world, and in fact, I wouldn't be surprised if here on campus most learning spaces are exactly like this one. I think around the globe, 99.9% of all learning spaces have this organization, focusing the attention of the students on one. And usually if you step into the classroom, you'll see a professor delivering information to students. We could well ask ourselves the question, is that what education is? Is education merely the transfer of information? I mean, that's not a crazy question, right? Because that's what we do. So on your screen is that question, answerable by a simple yes or no. Is education just the transfer of information? Or is education more than just the transfer of information? Let's see, somebody sent me a message here. What do we choose for a seat if we are online? Okay, thank you for asking that question. If you're online, you just say, I can't find my seat. If you do choose a seat, you'll be sitting in somebody else's lap. Okay. So, let's see what we have for distribution. What we have for distribution here. I only have about 3/4 of the answers in. It's not that hard. Either click A or click B. Go ahead. I'm going to give you 10 more seconds. We have an interesting distribution here. Usually it's slightly different, but that's fine. That's what makes it exciting. Here we go. I'm going to show you the results. And in case you don't have a device, this is what it looks like. We have 100% agreement. This morning was a much smaller group. I had 2 people who selected yes. I picked a little bit on them because I told them they would lose their job. Right? Because suppose for a moment that education would be just the transfer of information. What would be the logical thing to do? I beg your pardon?
Record a perfect lecture.
Record the perfect lecture and put it online, right? Why reenact the same lecture over and over again? And you can ask the best possible lecturers to lecture in the different languages that we need. What would you lose by doing that? What would you lose by taking the lecture and putting it online? Yes, of course. Absolutely. Absolutely, you'd lose your job. Besides losing your job, would you lose anything else? Interaction. But you know, how much interaction is there really in a lecture? You know, I'm working really hard on interacting here with you. We'll interact even more later on. But in a standard lecture, is there a lot of interaction? I mean, when you come into a classroom like this and you sit down in your seat, you're almost instantly put into a passive mode, right? You're put into a role of observer, not active participant. Most students come to class, they do not want to interact. I'm sure you've been in lectures where the instructor gives a brilliant lecture and then stops and says, does anybody have a question? Anybody? And you know how it is. Students look down because they don't want to make eye contact, right? And the lecture continues. And if you wait long enough so that it gets painful, it's always the same student in the front row who asks questions. So I think you would not lose much. Most students do not want to interact and do not interact. What would you gain? I think you'd actually gain a lot because you provide opportunities to think. You see, when you're in a classroom, there is no time to think because your brain is held captive by the continuous stream of information that comes from the instructor. If you start to think about something, daydreaming or whatever, you no longer listen to the incoming stream of information. Have you ever had in your class a student raise his hand and say, Professor, could you please be quiet for 5 minutes? I need to think. It's never happened to me. But online, or if you read a book, you can put the book down or hit the pause button on the display and actually think. Have you had a student raise their hand and say, Professor, could you please repeat the last 15 minutes? I need to hear it again. Maybe some of you have, but you know, I think it's very unusual to have that happen. Online, there's no problem. Rewind, play again. With a book, reread. Or you could pause your viewing and call up a friend and say, hey, do you understand what Professor Mazur says at 8 minutes and 21 seconds? So I think you'd actually create a lot of opportunities that are not there in the classroom. Besides, students can watch it whenever they're the most predisposed to watch it, not, you know, at a fixed schedule. So I think there are a lot of benefits. But I'm really happy to see that all of you agree that education is more than just a lecture. So let me ask you now, what is it more? What is missing? Go ahead. Well, come on, all of you said no, and now you can't tell me what more? Construction of knowledge.
You have to critically think of what you take in.
Think critically about the information you take in. Let's hear some more. Come on. We need to have some active engagement here. Yes? Application of the knowledge.
Assessment and feedback.
Assessment and feedback. There's still an exercise. Well, let's hear these two.
Ask questions.
I beg your pardon?
Ask questions.
Ask questions. The students to the instructor or the instructor to the students? I see. Okay, good.
I was going to say multiple viewpoints and discussion.
Multiple viewpoints and discussion, yes?
You can learn from everyone in the class, not just the teacher.
You can learn from everyone in the class. Very good. But think about this little exercise that we did. How did you learn that important skill or knowledge that you taught? By practicing. You need to do something. You need to be actively engaged. I think we heard a lot of things that were along the right track. As a learner, you need to do something with that information. It's not just a matter of putting the information in your skull, right? You need to connect it to the knowledge that's already there in your brain. You need to make sense of this information. You need to have this aha moment. Oh, I get it now. So much of education, if you stop to think about it, is instructors delivering information to students. Then you wait 1 month or 2 months. You separate the students from each other and from any source of information, and you have them regurgitate the information back to you. I was educated in Europe, and we tend to pride ourselves in high-quality secondary education in Europe. But if I stop to think about it, it was all really more like a house of cards, because I think I've forgotten pretty much everything I've ever learned, which when I read a quote recently by the famous psychologist Skinner, was actually reinforced. Skinner once said, "Education is what is left after all that is learned is forgotten." You're smiling about it. It's actually a pretty sad statement, isn't it? But, I mean, take history, for example. I was educated part-time in Holland, part-time in France, but when I was in Holland, the focus was on Dutch history, and at some point I learned in 1660-something, maybe somebody can Google, I've forgotten, I don't know, the Dutch defeated the British in the River Thames. And then a few weeks later on the exam, in what year did the Dutch defeat the British in the River Thames? I must have done well because I ended up in university. But if you stop to think about it, not only have I forgotten the year, I have no clue why the Dutch defeated the British in the River Thames. How it was possible for the Dutch to defeat the British on their own turf, right outside the capital city of London. Why in the world were they even fighting? I don't know. So, if you stop to think about it, however, I think a lot of education falls into that description of delivering information one way and then getting it back. You know, not that long ago, I was at a university in Connecticut, south of Boston, pretty well-known university, won't name any names. I was giving a talk about education, and after my talk, one of the faculty of the physics department came to me and said, "I've had something really weird happen this year in my classroom." He had wanted to make physics, he taught physics for engineers, relevant to the students. And in order to make it relevant, he had put it into a real-world context. And the context that he had used was baseball. I mean, there's a lot of physics in baseball, right? The trajectories of balls, collisions between balls and bats, runners running, and so on. So in class, he would use examples from baseball. On the homework, he'd put baseball problems. On the midterm examination, he had baseball problems. At the end of the semester, he was writing the final exam, and he realized he had run out of baseball problems. So he put some football problems on the exam. Professor, complained the students, "We have never done any football problems." You're laughing about it, but we should really be crying about it, right? You have to admit, if you cannot transfer what you've learned from one context to another context, you have not really learned. And unfortunately, I think most of our students even get uncomfortable when they encounter a problem in a new context. If I get a student who comes to me after an exam and says, "I've never done a problem like this," I always tell the student, look, if you had done a problem like this, it would by definition no longer be a problem. Right? A problem is not knowing how to solve something. However, this discomfort that students have in transferring their knowledge from one context to another is really a symptom that we're not teaching them the proper skills. So, what's the result? It took a long while for me to discover what the result was. In fact, what happened in my teaching career was that after I started teaching, lecturing, like I just described, I got signs that I was doing the right thing, because most students would give me high evaluations for my lectures. So I thought, Eric, you're a great lecturer. Not only that, these students would do well on some pretty darn complicated problems I wasn't sure I would do well on under the pressure of an exam. So in short, they liked me, they did well on exams. I was convinced that I was a good teacher. Now, in retrospect, there were always some negative signs, but I simply ignored them. You know, I'm a positive thinker, so if you get positive signs and negative signs, I ignore the negative ones and focus on the positive ones. Let me give you some examples. In spite of giving me high ratings, some students would write in the comment section of their evaluation, physics is boring. I could never, or physics sucks. I could never make any sense. I mean, what is more interesting than understanding how the world around us works, right? So I just simply ignore it. Same thing happens when I go to a party and people ask me what I do for a living, and I tell them I'm a physicist. They say, oh, physics, I had such a hard time with physics in college or in high school. So I decided, I basically ignored all these negative results, focused on the positive one. And for many, many years, I thought I was a great teacher. And it really took me more than 7 years to discover that my students were not really learning and were not really retaining the material, just like I failed to retain the year in which the Dutch defeated the British in the River Thames. The way I discovered it was as follows. In the early 90s, I read about an assessment instrument that tests students' understanding of the concept of force using just words. So rather than a typical textbook problem that used equations, this used just words. And the author of the test showed that in the southwest of the United States, Arizona, New Mexico, California, and Nevada, students do equally poorly at the end of a semester of physics as they did at the beginning. There's hardly any difference in the way they answer these questions. And the questions deal mostly with the concept of force, which is one of the most basic concepts in physics. If you don't understand force, you cannot really understand more advanced subjects. Well, when I read that, I thought this doesn't apply to me, but what intrigued me was the fact that he showed that the gain, the pre-test to post-test gain, pre-test meaning at the beginning of the term, post-test at the end of the term, was no different for award-winning teachers than for dull, dry, boring teachers. Well, I thought that's impossible. First of all, I knew I was a good teacher. Secondly, I thought, I'm in the Northeast. All these data are from the Southwest. Maybe there's some disease raging in the Southwest of the US. I'm going to show that in my class it's different. Hardly had my students started to take this test, or one student raised her hand and she said, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? I had no idea how to answer that question. And by the time the test had been completed, I had been dragged out of my ivory tower. And it was clear that in spite of my high evaluations, in spite of my students being able to solve textbook problems, they were not really internalizing even the most basic things. I struggled with that a long time. First I thought, Eric, maybe after all you're not such a good teacher. But that could obviously not be true, right? So I discarded that possibility very quickly. Then I went through this phase that I thought, I must have really dumb students. But you know, at my institution, that's a hard claim to make. So then I thought, oh, there must be something wrong with the test. And I started to do some testing of my own by, on exams, putting a textbook problem together with a word-based problem on exactly the same subject, only to discover that the students would be able to do the textbook problem, but not the word-based problem. Why? Because they had learned to solve problems by rote. They were simply following cookbook strategies. And that's why they were unable to transfer their knowledge to new context. So, whoops, what is that? Okay, let's forget about this. I wanted to show you a little movie, but I'm not going to do it, which is a solution that was proposed. I'll describe it to you. In the 70s, for those of you who watched Saturday Night Live, it was already a popular program back in the 70s. And back in the 70s, there was this character called Father Guido Sarducci. Some of you may know him. And back in the 70s, he came up with a proposal on Saturday Night Live, which I think is a very good proposal, for the 5-minute university. The 5-minute university has this basic idea. Teach in 5 minutes what the average college graduate remembers 5 years after graduating from college. Why waste time, memorizing and learning all these things that you're going to forget anyway? For example, if you want to learn Spanish, right? It's very simple. You say, ¿Cómo está usted? And the answer is, muy bien. And after all, 5 years after taking Spanish in college, that's about all you're going to remember anyway. So why waste time on all the other things? I mean, we're laughing about it, but there is, at some level, some truth to all of this. Okay, so when I discovered that my students weren't learning, and when I finally could no longer refute the evidence that was staring me in the face, for a moment I thought, well, Eric, maybe you should only teach graduate courses. But it turns out that the solution presented itself completely serendipitously. After they took this forced concept inventory, this test, this word-based test, not only was I horrified, my students were horrified too. And they asked me for a session in which I would discuss every single question on that test. And I remember coming to one question that was dealing with the forces exerting by a heavy truck and a light car when they collide head-on. And I basically drew the forces on the car, the forces on the truck, and I said, by Newton's third law, the force of the car on the truck is equal to that of the truck on the car, which was what the question was about. What more is there to explain about it, right? So I turned around after drawing these 3 body diagrams. I looked around, and I could at once see from the faces of my students that they didn't get it. So I said, is there a question? They were so confused they could not articulate a question. Well, I knew this was serious, so I thought, maybe that they think the heavier object exerts a larger force on the lighter car on the lighter object because the effect on the lighter object is bigger. So I thought I need to really bring in Newton's second law too. So don't worry about the details because this talks not about physics. But I erased the board, and in 8 minutes I gave the most brilliant explanation you could possibly imagine. And after 8 minutes the board was covered with equations, Newton's third law, Newton's second law. Anyway, I turned around triumphantly, my coat jacket covered in chalk dust, only to see that they looked even more confused. And they could still not articulate a question. I knew one thing. I knew that about half of them had given the right answer to that question. So in a moment of despair, I said, why don't you discuss it with each other? And something happened I had never seen before in my classroom. The entire classroom erupted in chaos. They forgot about me in front. I could have walked away. They wouldn't have noticed. And what's more, in just 2 minutes, they figured it out. I thought, how can that be? I've just tried it for 10 minutes unsuccessfully to explain it, and in just 2 minutes, they figure it out. But imagine you have 2 students sitting next to each other, John and Mary. Mary understands it and has the right answer. John does not understand it and does not have the right answer. On average, Mary is more likely to convince John than the other way around, simply the force of logic. But what's more important is that Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it. She still knows what the difficulties are that a beginning learner has. Whereas Professor Mazur learned it such a long time ago, to him it is so clear that he cannot even understand why somebody doesn't understand it. It's what Steven Pinker calls the curse of knowledge. Right? I'm making sort of a strange argument here, right? Because you tend to think the more of an expert you become, the more qualified you are to teach it. I'm making sort of the inverse argument here. Because we tend to forget what the difficulties are that the beginning learners. Once you understand it, all the difficulties vanish. So when I saw that, I thought, wow, maybe I can exploit this in the classroom. And if we go back to what we said about education, transfer of information is definitely an important part of education. No transfer of information, no education, right? I mean, we need the transfer of information. But as we established, we need more than that. We need to give the learners an opportunity to assimilate that information. To get the aha moments, I get it. Where did that happen for you? I've often asked myself that question too. Where did it happen for me? Did it happen while you were sitting in a classroom like this? Did the aha moments, oh, I get it, happen when you were in class? Maybe occasionally. But I would say most of it happened outside of the classroom. So in the standard approach to teaching, we focus all of our efforts on the transfer of information, and we leave the hard part, the assimilation of information, to the students, often on their own. I think you all agree we should actually really focus on that second step, not on the first step. So back then, I decided what I should really do is invert this approach. Rather than doing 1 in class and 2 out of class, I should do 1 out of class and 2 in class. Well, there are lots of ways of transferring the information nowadays. And in fact, MOOCs are one attempt to do that. Unfortunately, people think that they will have solved all the problems in education by that. But to me, that's the easy part. Transferring information is not the hard part of education. It's that second step that is important. So I'm not going to talk about transferring information out of the class. I'm only going to talk about what do we do in class if the information has been transferred outside of the class. So now what I do is I ask my students to read a textbook before class or to watch a lecture I've given on the subject before. And we can talk later about how to make sure that they actually do that. And then in class, I teach by questioning rather than by telling. Incidentally, that is absolutely nothing new. Who said that first? Socrates, 2,000 years ago. And here we're in the 21st century, and we're still mostly teaching by telling rather than by questioning. So I'll walk into class, I'll talk a few minutes, and I ask a question. And after I ask the question, I give students an opportunity to think. It's completely silent. After their thought, I poll them for their answers. And then I tell them to find a neighbor who has a different answer and to try to convince that neighbor of their answer. So they'll start talking. And I poll them again, usually with significantly larger number of correct answers. Then I have either one of the students provide an explanation or I provide an explanation, and I repeat from the start until class time is up. And of course, the learning, the assimilation, the aha moments take place during that discussion stage. So let me show you a little video of my classroom of what this may look like in an environment that's actually not very different from this, because I do it in a standard classroom. So we have a rectangular loop that is placed in a uniform magnetic field in the direction indicated by these arrows. So the question is, what are the magnetic forces on the 4 different sides of this loop? Take a minute to think about this and then enter your answers. Please enter your answers. We have a Simon disagreement clearly here. So turn to your neighbor and see if you can convince one another of the correct choice.
Right. It goes out of the page and the top goes in, so they cancel each other out.
There is a torque.
There is a torque.
How do you know that?
I said torque.
You can see the data streaming.
But how can it be a torque? Oh, so it was weird. So I didn't know. How does it affect?
Initially, we had sort of an even split. And now we have an absolutely overwhelming majority for choice number 2. The bottom of this loop is pulled towards you. The top is pushed away. What is that? A net torque. We seem to have lost the people online. I guess there was too much demand of the live cast, so I'm being inundated with messages here. Anyway, 2 things you saw here. One is it's active, not passive. There is absolutely no way to sleep through my classes because every few minutes your neighbor will start talking to you. Believe it or not, some students complain about that. Secondly, there's a 2-way flow of information. It's not only from me to the students, there's information coming back. If they don't understand something, I can tell then and there because I see it on my screen. I don't have to wait till the homework or the midterm examination to find out that there's a problem. I can do something about it immediately. Lastly, it provides the students a continuous opportunity for formative assessment. They get to try out their knowledge. There's immediate feedback to them. They don't see the first distribution. You saw 2 distributions, one before discussion where choice 1 and 2 were about equally distributed, and one after discussion where one choice, I forgot which one it was, 2 went to 90%, the correct one, and the other one went to 10%. If you're, that one I do show. I don't show the one before discussion, but I do show the one after discussion. So imagine you're a student in the class and you voted 1, which only 10% of the students said is wrong. There's no penalty for it, but at least you get feedback on your knowledge. You get to try out your knowledge continuously. And you may do something about it. And people have pointed out the importance of formative assessment, of which we actually do so little. Assessment that is focused on feedback on the learning rather than on classifying and ranking students. So it's a very different feeling. Let me go through a slightly different flowchart so you see in a little bit more detail of how I run it. So I speak a few minutes, never more than maybe 5, much shorter than I did here. Then I pose a question, and I poll them. If more than 70% have it correct, then it doesn't make much sense to have them talk to each other, right? Because they're going to talk to their neighbor and find out that most of the neighbors have the same answer too. And they're going to start doing something else. They'll go off task. So basically, the question was too simple. So I have one of the students provide an explanation, and then I repeat from the start. If between 30 and 70% have it correct, that's perfect. I ask them to turn to each other, discuss. Then I poll them again, I explain, and I repeat. If less than 30% have it right, then it doesn't make much sense to have them talk to each other because there's simply not going to be enough students who have the right answer. So basically the question was too hard. I revisit the concept and repeat with an easier question on the same subject. Of course, the ideal pathway, the one in which the most learning takes place, is the one highlighted there in the middle. Do you want to try it? Yeah? Are you ready to try it? Boy, you're an awfully quiet audience here. I'm going to have to do something like that. Did you all, I asked Professor Bates to hand out 2 paragraphs about thermal expansion. Did you all read that? No? I mean, how can I demonstrate this if you haven't done your reading? I'm just kidding. I'm just kidding. But you know what that means? That means that I'll have to lecture you about thermal expansion. Actually, I'm very grateful because the one thing I miss about peer instruction is that I don't get to lecture. So at least I can make up for some of that loss here. So we're going to talk about thermal expansion. Thermal expansion is the expansion of solids as the temperature rises. So all solids have a larger volume when it's hotter than when it's colder. So if you heat them, they expand. If you cool them, they contract. It's true for all solids, and it's particularly pronounced for reasons that don't matter in metals. And it's very important in engineering, right? If you're in a train, you may have noticed that at low speed, you hear this clickety-clack sound when the wheels go over the gaps that are between different sections of the rail. You may wonder, why don't they jam the two sections together? Well, if they do that and the weather heats up, you get bad things like here. The metal will expand, there's no space to expand, and therefore it will buckle. Likewise, in steel beam buildings, you need to take into account the expansion of metal beams, which is more pronounced than that in, let's say, concrete or plaster. If you don't do that, you get cracks and other kinds of problems. So in engineering, this is an important thing. You may wonder, why is it that metals expand well, or solids, pardon me, because it's not only metals, it's all solids. Why do they expand? Well, they expand because they're made from atoms, and atoms get further apart from each other when they get hotter. So this is cold, and this is hot. Cold and hot. That's all. Cold, hot. You may wonder, why is it that they get further away from each other? I'm not going to test you on this, but let me explain it to you. The reason is that atoms don't sit still. They move, and the amplitude, we call that thermal motion. And the amplitude of that thermal motion is what we call temperature. So these are cold atoms, and these are hot atoms. Now, atoms attract each other, so they're close together. So at low temperature, they vibrate like that. But at higher temperature, as the amplitude gets larger, they're pushing each other away. Not just those 9. All of them. All millions of billions of atoms that make up a solid. Cold, hot. Questions, anyone? Questions? Oh, yes, good. Gases and liquids are also made of atoms, yeah, but in that case, they don't hold each other in a fixed pattern, and in gases, they're actually fairly far apart. But we will not talk about gases and liquids. We'll only talk about solids. No questions? I knew I gave brilliant lectures. Okay. Now, I have to warn you. I'm not going to blank out the screen and then ask you the question, when metals get hotter, they expand because A, atoms get further apart, B, they stay the same distance, C, they get closer together. That would be simply me delivering information to you and you delivering that same information back to me. I'm going to see if you can take this idea of the atoms getting further away from each other, all of them, if you can apply that into a new context. So you better ask me questions. Cold and hot. No questions? Wow. How come the center one is not moving? Good question. I was waiting for that question, actually. How come the center one is not moving? Well, the reason is because I made 2 drawings of 9 atoms. And I put the 2 drawings on top of each other, centering that central atom on top of each other. But that's an arbitrary choice. I could equally well have pinned this atom down. What would this atom have done then? It would have gone down and to the right. And this one, instead of going up, would have gone to the right. And this one would have gone twice as far to the right. And this one would have gone twice as far down and to the right. So in other words, it's not really the absolute position of the atoms that matter. What matters is that they all get further away from each other. So thank you for asking that question. Yes?
Did you say that when they were cool, they attracted each other, and when they were warm,
they always attract each other. So as the amplitude of that motion diminishes, they can get closer together. Yes?
You said at the start of the lecture that metals, this problem is more pronounced. Is that possibly because the metals somehow, the atoms align and they move more together in the same direction rather than...
No, there's much more that comes into play to explain that. And this is so way beyond what I'm going to ask you that if you want to talk about it, we'll talk about it after my talk here. And we're done? Are you ready? Yes.
Is there a way to limit the movement or control it?
Is there a way to limit the movement? I'm not 100% sure what you mean, but if you keep raising the temperature, right, they push each other further and further apart, and at some point the attraction is no longer strong enough to hold the atoms together, and what happens is you melt the solid, right, in the case of a metal, for example, or ice. But maybe what you're referring to is, suppose you put an outside constraint on it, right? Let's say we take those 9 atoms and we put a box around it and really try to, you cannot. These forces are so large, it'll push everything out. Okay, wow, now we get questions. Go ahead, you, then you, then you.
What if you took your solid and cut it in half and separated them by a small amount? Then not all the atoms would get further apart. Some of them would get closer to each other from what I'm
Sorry, I'm not exactly sure what you mean. We take those 9 atoms and let...
If you have 2 objects that are close together,
yeah,
and you heat them both together,
yeah,
then you're sticking all of the atoms get further apart from each other.
Right. So what it would so let's say this is one object, that's the other, right? And separately they would each do this. If they're together, they're pushing against each other here, so they would push out from that central line. But all the atoms would still get further away from each other, including the ones that are touching each other from the different objects.
But if they're separated, that's not.
If they're separated as in?
If they're separated, then not all of the atoms get further away from each other.
Oh, I see. So, for example, suppose you have 2 parts of metal here, and this expands and that expands, then the atom on the leftmost edge of this get closer to those on the... Yes, absolutely. Yes. Thank you. You must be a lawyer. You stick to your points. Okay. It will. It will. And the final exam is coming very soon. Last question.
Ice at 0 degrees, the minimum density is at 4 degrees, which is higher in temperature.
Yes. So there's something funny with ice. So if you have a soda in front of you with ice floating in it, the ice floats. The ice is solid, which is colder than the drink, which is not at 0 degrees. So what's happening here? Well, water is a peculiar thing. But let's first talk about ice itself. If you take ice, because I'm only talking about solids, right? Now we're comparing solids and liquids. If you take ice and you cool it down below 0, let's say to -10, it shrinks. And if you heat it up to -5, it expands. So ice follows exactly the same trend as a metal or any other solid. The peculiarity happens when it melts, when it transforms from a solid into a liquid. And because of hydrogen bonds and the shape of the water molecule, the liquid is actually denser than the solid. But that's a peculiar... I'm not going to trick you with that type of thing. Are we ready for the question? I think we're ready, huh? Yeah. Okay. So consider a rectangular metal plate with a circular... Wow, I haven't even asked the question and somebody's answered it already. How can it be? Consider a rectangular metal plate with a circular hole in it. When the plate is uniformly heated, the diameter of the hole, 1, increases, 2, stays the same, 3, decreases. Now, don't talk to your neighbor. If you talk to your neighbor, I will come to you with this microphone, and I will ask you to say in front of everyone what you're saying. So, individual commitment. So if you already answered, and I already have quite a few answers in, don't sit there idle. Just ask yourself, how am I going to convince the person next to me that my answer is right and his or her answer is wrong? So ask yourself in terms of the atoms getting further away from each other. No talking yet. You get a chance to talk to them. Okay, 20 more seconds. 15. 10 seconds. So by now, if you don't know yet, just make it a guess. Make it a game. It's you know, nothing depends on whether you get this right or wrong. But I do want you to commit to an answer. So you get 5 more seconds here to respond. I still need about 30 answers in my system here. 4, 2. Okay, so now the instructions are find a neighbor who has a different answer. Don't talk. If you turn one way and the person has the same answer as you say, thank you very much, and you turn the other way. If you sit without talking to anyone, I will come and talk to you. Go ahead, talk to each other. Test 1, 2, 3. This is on? Is this on? Okay! I think my microphone died. I couldn't even get your attention back. You all got fired up. It's just a hole in a plate. I mean, imagine I'd given my little lecture. There's still some people talking there about the holes in the... Imagine I'd given my little lecture about thermal expansion, and then I'd said, it's okay, you get to talk. Hello? They don't even notice me. It's okay. Imagine I'd given this little lecture, and then I'd said, let's now apply it to rectangular plates with circular holes in it. If you take one of these rectangular plates, and you put it in the oven, and you raise the temperature, the plate will expand. God, I love this attention that we're having here. The plate will expand, and the diameter of the hole will... I'm going to keep you in suspense a little bit longer, but you know, you would not have gotten this excited about it. What is more boring than rectangular plates with circular holes in it, right? Now, before I tell you the answer, let's analyze what happened here, right? 1, you made a commitment. I had you answer what you thought was the right answer. And then after that, I asked you to turn to a neighbor at a different answer, and you had to externalize your answer. You said, I chose answer because blah, blah, blah. And in the process, I was listening in to some of these discussions. You moved from the answer or the fact to reasoning. You said, I chose this because blah, blah, blah. You started to think like a scientist, like a physicist. It was no longer the answer that was important. It was the reasoning that became important. But most of all, you became emotionally invested in the learning process. If I were to tell you now, oh, God, I've got to make my flight. Sorry, I have to leave. You'd come running after me asking what the answer is, right? Now, before I can tell you what the answer is, you need to answer it again. So please re-answer the question. Tell me what you now believe to be the correct answer. So answer it again. Even if you've not changed your mind, please answer that same question again. I bet that the answer to this question really doesn't matter. We've already made the important point. Right? The important point that I've made here is that it is very easy to reawaken the curiosity of the human mind. I mean, you're not going to get a salary increase or a bonus or a grade or a certificate for getting this question right. Yet, you're all desperate to know what the right answer is. In education, we do a very good job, starting in secondary education, turning off this curiosity that we're all born with. We only have to look at small children to see, what a sponge they are for learning. You can't stop them from asking why and how and wanting to understand and learn and master. And then we get to secondary education, and all of a sudden we're told what to learn and told what to do and told what to memorize and regurgitate, and the curiosity is turned off. But as you saw, it's really easy to turn it back on. Okay, I think most of you have re-answered it. Yes, that's correct. And you know what? I have some bad news for you. I thought I gave a pretty darn clear lecture about thermal expansion. Only 40% of you got it right the first time, which means out of every 3 people, only 1 got it right. That's marginal, you know, because it's hard to get big improvements when you have only 30%. So you've already made a really important point. You've basically been telling me, Eric, your lecturing sucks. Well, after all, but really, you should have done your reading. That's the real problem. You should have come prepared to class. So let's see what the distribution is now. I'm going to show you the data. And for those of you who don't have a device, there they are. Initially, we had 40% correct. We had a majority of the answers for it goes, the metal expands into the hole and the diameter decreases. Now we have a majority for the correct answer, which is answer number 1. Oh, I can hear people start talking again. You know, I don't want you to lie in bed tonight, awake at 2 a.m. thinking, you know, why is this hole getting larger? Well, imagine you have a jar of marmalade, glass jar, metal lid. The lid is a ring and a metal plate. It's in the refrigerator. You take it out of the refrigerator. You try to open it. You can't open it. What do? You run it under hot water, and the ring expands, so the opening gets larger. You say, that's unfair. You did not ask us about lids of jars. Okay, imagine we have a metal plate, no hole in it. There's the rectangular metal plate, no hole in it. We take out a marker and we draw a circle on that plate. Now we put the plate with a circle on it in the oven. It expands. What happens to the diameter of the circle? It gets bigger, right? Everything gets bigger, so the circle gets bigger. You say, that's unfair. There's no hole. If there was a hole, then the metal would expand into the hole. Okay, well, imagine we go outside. It's a pretty nice day, and we hold hands, all of us. We are the atoms at the edge of the hole, holding hands like this. And now we all step in towards the center of the circle. What just happened to the distance between us? It gets smaller. We get squeezed together. We can't get squeezed together because our neighbor is shaking more, remember? The only way to make the distance larger would be to remove a few of us, but atoms don't disappear like that, or to make the circle larger. You won't forget this. Okay, back to peer instruction. You know, I really, normally when I give a talk about peer instruction, I show data, because I think it's so important in education to actually back up claims with data. Even in science departments, so many discussions about education are purely anecdotal. My students learn better when I do this or that. Or my students really like it when I do a lot of demonstrations. Hell, maybe they like it, but do they actually learn better? I like whenever my colleagues, and I have quite a few colleagues who are guilty of this, start talking about education in anecdotal terms, I like to quote to them Lee Shulman, who was the former president of the Carnegie Foundation in the US. He once said, and it's a very simple quote, "The plural of anecdote is not data." You don't validate a claim just by saying anecdotes. And unfortunately, I don't have time to show you data, but if you're interested in the data, they're available in the papers on my website, or you can see on YouTube a talk called Confessions of a Converted Lecturer, where I have plenty of data. But both my group and many other groups in many different fields, including fields I would have never expected. You see, the question that I asked you had a right or wrong answer. There might be quite a few people here in the humanities who are wondering, you know, can I apply this in my field? The questions don't have right or wrong answers. And the answer is yes. Because even in your field, there's critical thinking. And let's say that you're teaching literature, or let's say that you're teaching art history, right? And you're discussing the interpretation of a painting from the Renaissance. One of the ways to do it is to show the painting and then to give your interpretation of that work of art. the artist is long dead. There's no way that we can ask him about the meaning of different symbolism in the painting. And if you look in the literature, different scholars are actually in disagreement about the interpretation of that painting. One way would be for you to present the interpretation. The other would be for you to give the students an opportunity, A, to commit to an interpretation, and then discuss the merits of these different interpretations with other students. And in the process, rather than accepting you as the source of authority, they get to form, or to develop, I should say, the skills that they will need if they are to become successful art historians. And I think the same will be true in psychology or literature, or you name it. So I think the method can really be applied in all fields where either model building or critical thinking or interpretations are involved. If you just teach fact recall, then I don't think this method will add very much, but I would be really surprised if any of you is interested in teaching just fact recall. So, higher learning gains, better retention. Unfortunately, I have no time to show that to you because I want to get to the fun stuff. If you're interested in peer instruction and you're curious about who is using it, there's this social network of peer instruction users that you can join and then query to find other people in your discipline or institution who either may already been using it, but have used it, or interested in using it. So let's next move to PI 2.0. Because a lot of peer instruction is hinged on feedback, right? Feedback from you to me. When I started with peer instruction over 20 years ago, there was no technology. I simply used a show of hand or flashcards also. You know, we could have done this question about the hole in the plate by simply having you put your hand on your chest, showing 1, 2, or 3 fingers. Right? I could have said, at the count of 3, everybody put their hand on their chest with the choice you've made. And I would have told you, if you don't put your hand on your chest, I want to come to you. I'm going to put this microphone in your face, and you're going to tell everybody. When you tell that to students, they immediately put their hand on their chest. As an instructor, you see the distribution. As a student, you don't see the distribution because you look at the backs of students. So it's a way of anonymously voting and still getting the feedback. So, you know, what we did does not depend on technology. It's a pedagogy that's important, not the technology. But I love technology, and I'm an early adopter of technology. So back in 1993, I developed a wired network of calculators. I worked with people who were developing it, called ClassTalk, and we had a classroom equipped with it. It was beautiful. It was extremely expensive, and it was wired, so it was not very convenient, but I could get the identity of the students, the seat map, everything. It was gorgeous. But it was impossible to scale up because of the cost, and it was incredibly hard to maintain. At the end of class, students would just get up from their seat, walk away, forget to unplug the cable, and just destroy the whole network interface. So that was not the best solution. But in 1998, an alum of the School of Engineering and Applied Sciences at Harvard developed the first infrared wireless clicker called PRS, or Personal Response System. And then something really amazing happened, because in the next 10 years, a zoo of clickers appeared. Well, a small zoo, but it's still a zoo nonetheless. Lots of different clickers, some campuses even adopting different standards. And something interesting happens. Incidentally, right now, the clicker market is a $100 million a year market. Right? Yeah. And something really interesting happened, because all of a sudden it became all about the technology. People did not adopt the pedagogy, they adopted the technology. And I would have actually instructors come to me and say, oh, I've adopted your clicker technology. And I would get mad. First of all, in my mind, it was not about the technology, but about the pedagogy. And in fact, many instructors were using the clickers completely incorrectly. They would lecture like they did before, and then they would ask a fact recall question, like, which of the following is not a living being? A rock, a giraffe, or a flower? And the students click 1, and the instructor says, good, let's continue. Right? No peer and peer instruction, nothing. So that was one reason that bugged me. But the other was, I failed to commercialize it myself. So I missed the boat on that completely. And in giving workshops on peer instruction, I noticed that the real questions that instructors had was, how do I design good questions? How do I optimize the discussions in the classroom? How do I manage time? None of the systems that I'm showing on the screen there offers an answer to that question. So that's when, together with a colleague at Harvard and one of my postdocs, we founded Learning Catalytics, which you've been using. It was founded literally only 20 months ago, and it was sold 3 months ago to Pearson, so it's no longer my company. So basically it's Gary King, who is a statistician and who does data analytics on social media. Brian Lukoff, who was a postdoc of mine, who got his thesis at Stanford on a very interesting subject. He got it in the Department of Education, working on machine interpretation of drawn graphs. So in other words, you could get students draw graphs, and he could actually score how accurately that graph represented a mathematical function. When I saw that, when I saw him give a talk about his thesis, I thought, wow, that's great, because this could be used as a response mechanism for non-verbal, non-multiple choice questions. And Gary King, who was my mountain bike buddy actually, we started 2 other companies at the same time, and I didn't know exactly what his company was doing. It's called Crimson Hexagon, and what it does is analysis of social media. So he basically gets the Twitter feed and can do sort of cluster analysis to do certain things. Like, for example, in 2008, during the presidential election, by analyzing tweets, he was able to predict the outcome of the election county by county simply on what people tweeted. So I thought, wow, if you can do cluster analysis on social media, which have just any format, then maybe you can do the same thing on free response answers that students type in. You might not get exactly accurate data, but at least you get a feeling for what students are answering. So that's when we decided to put our efforts together and to use intelligent algorithms and data analytics to, 1, improve the questioning, 2, manage the discussions, and lastly, to facilitate the time management in the classroom. So let's have some fun. And we're not going to do this in pre-instruction mode because it would simply take too much time. I'm going to show you different question types, because basically, what is one of the big problems that we have in teaching with clickers or a lot of assessment in general? It is the fact that we use multiple choice questions. And multiple choice questions are inherently hard to design. If you have a multiple choice question, it's usually easy to come up with the right answer, or at least the intended answer. It's hard to come up with plausible wrong answers. The only way would be to do research, namely to give the question as a free response question, tabulate for thousands of students what the incoming responses are, classify them, and then construct a multiple choice question from that. But we don't have time to do that, right? I mean, if we did all of that, we'd be spending our lives designing multiple choice questions, which is why most multiple choice questions that are used, like the ones that I'm showing here, which have to do with accounting, are pretty meaningless, because you can, as a student, often work by elimination, because the answers do not correspond to the type of misconceptions or thoughts that you have in your mind. So we decided to use an extensible plugin architecture for many different question types. You've already seen one, the word cloud, and you've seen the multiple choice, but there are many that include things like mathematical expression, direction, graphical, and so on. Let's have some fun with a few. And if you've not yet on, the instructions are at the bottom. Go to learningcatalytics.com, create a student account using the free sign-up code DEMO, and then enter the ID 1234567. So this picture here that you see on the screen is a picture of Oahu taken from the space shuttle 300 kilometers up, which is why it's not that sharp. Here you see Waikiki, Diamond Head. This is Pearl Harbor. And you can see clouds, that's the white stuff there. And you can see that some parts have lush vegetation, other parts of the island are very dry. If you look at this picture, it has clues about the prevailing wind directions in the Pacific. I want you to, on the screen in front of you, if it's a touch screen, just with your finger. If it's a trackpad, with a trackpad, draw an arrow indicating what you believe to be the prevailing wind direction, and then hit submit. And if you've done that, I'll show everybody. I'll project it in a minute. Okay, so I basically see the same question as you do, but next to it I see a little drawing which has the same picture with all of the arrows that have been drawn. I'm going to give you a little bit more time. Actually, why don't I show it to you? Here it is. Here you can see it. Here's the little... And you can see that people have arrows in all different directions. I'm going to stop it and show it on your own screen so you can see what it looks like. So I use this, for example, with questions in optics. This question deals, and I'm not going to send it to you, I'm just going to show it to you, with an incident ray that hits a set of two mirrors, mirror 1 here and mirror 2, which are at right angle. Using the law of reflection, which I'm sure many of you don't know, but it doesn't matter, and simple geometry, you can show that the ray, after bouncing twice, goes straight back, regardless of the orientation of those two mirrors. I used to ask this as a multiple choice question. But when I designed that multiple choice question, I had no idea which direction to draw my rays in. So I just drew a couple of random rays. With this system, there's no need to do that, right? You just have the students draw a ray, and then you see all of your students' rays. This is actually from my introductory physics course. And as you can see, there's a very strong misconception that the ray is going to come in below the horizontal. I would not have predicted that. Why? Because I know that it's coming straight back. I'm no longer able, again, the curse of knowledge, I'm no longer able to predict that misconception. And then I have the students talk to each other, and you get a far smaller, we're here up to 73% correct, a far smaller number of wrong arrows and many more correct arrows. Let's have a different graphical question. We're going to a very different field here. We're going to art history. On the screen in front of you is a painting by the Renaissance artist Sassetta, and it shows a number of people. Which of these people is St. John the Baptist? So go ahead. You just indicate which person you think is St. John the Baptist, and then you hit submit. It never fails. It never fails. There's always some people who choose the infant Jesus. At least we have no people who chose the Virgin Mary. Let me show you what it looks like. I'm going to show you on your screen what it looks like for those of you who have no device. Here it is. There we go. Right, so if you indicate the right... I've seen biologists use this to have students look at ion channels in cells, parts of neural networks, and so on. I mean, there are many different ways you could use it. Or you could use it in the teaching of calculus to have students identify certain parts of functions, and so forth. Right? Okay. In addition to that, it has a full mathematical engine, so it can actually interpret mathematical expressions. And with mathematics, it's not that simple, right? Because let's say that the answer you're after is A plus B. B plus E is also correct. And 2A plus 2B divided by 2 is also correct. Or A plus B plus C minus C is also correct. There are many different mathematically equivalent ways to express the correct answer. Let's try this. And I know people, it's Friday afternoon and people are tired, so I'm asking you a really simple question here. If 2x minus y equals 4, then what is x? So enter an answer, and I encourage you to challenge the system by entering the answer in what might not be the most logical way. But mathematically correct, of course. Okay. So, We have about 60% of the responses in, and I'm pleased to report 57% correct. Maybe we should do some P instruction. But we have a lot of different ways of expressing the correct answer. I'm going to display it on your screen now. So it should be on your screen. And I'm also going to put it here, just so you see it. Is it on your screen? No. What about now? Yes. So here's one way of expressing the right answer. 18% of people had that. 4 plus y in parentheses divided by 2. But you can work out the parentheses, 2 plus y divided by 2, or you can just add 12, subtract 12. Or look at this, or here, take the logarithm of the square root here. Here somebody wrote x equals, even though it's not necessary to write x equals, but didn't get penalized for that. I'm sorry, 4 is not correct. And some people challenged themselves trying to challenge the program. Incidentally, why is this one incorrect? Uppercase. Yeah, it's case sensitive, which is important because in a number of disciplines like physics or, accounting or finance, you might use an uppercase symbol to mean something very different from a lowercase symbol. But this is a really fantastic tool to test students' understanding. You can have them work out a problem, and then no need for multiple choice. The system will actually interpret. Same thing with numerical. Units, same thing too. If, let's say, you ask them to calculate the magnitude of a force, and it's 4 Newton, then students could either write 4 Newton, or they could write 4 kilogram meter per second squared. The system knows how to convert SI units, or units in general, and therefore it no longer is dependent on how students enter the units. If they omit the units, that's bad, because then it's not counted as being correct. Other types of questions would be graphical. For example, here, this function is the logarithm of x. So you can show it to the students and ask them to draw the derivative. And then as an instructor, you can see the different functions that your students draw. Now, that's fine if you have, 3 times 5, 15 students there. But what if you have several hundred students? Let's try it. I'm going to show you a little story on your screen. Here we are. Sarah rides her bike to a friend's house, which is half a mile from home. A straight road along which she rides at a steady speed leads from her home to her friend. The trip takes 5 minutes. She stays at her friend's house for 5 minutes, then walks back home at half the speed she had on her bike. Sketch her position as a function of time on the graph below. Okay, I'm going to stop delivery and show the results. So here you can see that most of you got the right answer. Some people forgot the 5-minute break at her friend's house. Other people somehow miraculously went from 0 to half a mile instantaneously. But you can see that the overwhelming majority has the correct answer. Okay, a few more before we go and wrap up here. Let's have some fun with statistics, right? I mean, who thinks of statistics as being fun? I want you to take a coin, to toss it 6 times, and then enter the number of heads you have obtained. Somebody immediately entered 5. How can that be? This never fails to amuse people. You can see the Gaussian being built up. The median is 4 right now. You can see the standard deviation, which is pretty close to the standard deviation of a Gaussian. What field are you teaching?
I did physics.
You teach physics. You can see you can see a Gaussian slowly coming out here, and you can see the standard deviation 1.16,
Yeah.
median 3.
But you see, for myself, I know that I cannot see on this. For me, it's small. So if I were to come to class, I would have
We've brought an iPad. Okay, well, I can tell you're having fun. I'm going to show the distribution here. So there we are. Median 3, standard deviation 1.15, which is pretty close what you would expect if you had a Gaussian centered around the median. So you can sort of see the Gaussian being built up here. And there are lots of similar data acquisition questions that you can use for demonstration purposes in class. Which one is correct? There's no correct answer. Let's do one final one that will appeal to the people in the humanities. I'm going to show you a little poem by Stephen Crane. I want you to read that. Fast Rode the Night. And then highlight the line, or lines plural if you want, but they have to be contiguous, that you feel has the strongest imagery in that poem. Right? So go ahead, read it. You highlight the part that you think has the strongest imagery, and then you hit submit. Actually, there's a different poem from the one on the screen is Shakespeare. And the people who are online, there are many people online who are entering questions or sending me messages here, but I cannot process that while I'm talking. So I think we have another channel, right? Where should they submit their questions? On there?
Comment field.
Oh, use the online comment field where you are watching, not in Learning Catalytics, because I can't process the incoming stream of questions. So, just to describe what's happening here, as what I'm seeing on my iPad here is a heat map of parts that are selected. So the whole poem is grayed out, and as people select the same part over and over again, it becomes brighter and brighter. So the brightest spots are those that have been selected the most. So for example, with this poem from Shakespeare here, you know, a student highlights a sentence, and then as an instructor, I get sort of a heat map as shown here, where most of the students, what they interpret as being the most important, or whatever else you ask. Here, for this question, we are only about half the questions in, but I'm going to stop it here and show all the results. We have several parts of the poem that, in particular here, blowing, staggering, bloody thing. And some people selected this part. The by the way, that's just an artifact of the program. Okay, so you get an idea of the different types of problems which can appeal to many different fields. And in the back end, there's data analytics that I haven't even been able to talk about because so much data in education gets thrown away, right? You use clickers, you get data, they go into a black hole. You may look at it once, but you don't know what to do with it. Here, all the data get aggregated, so you can compare your students to the performance elsewhere. The questions are, there's a huge database of questions. If you enter a question and you indicate that you're willing to share it, other instructors can see your question, and you get to see how students at other institutions do on your question. So those historical data are available. And ultimately, we want to be able to suggest questions that work well in a given environment, right? Because if you ask a certain number of questions in your class, the program can look at other classes that have done like your students and then suggest other questions that might work well. Much like Amazon has this, what is called cooperative filtering, where you shop for something and it says people who have looked at this have also bought these different things. And I think that should be helpful in finding the right material. But let's talk about something else here, because all of this really hinges on the interaction between the students. We have not done any peer instruction here, right? What we did the last half hour was simply having fun with question types. We haven't done anything that is pedagogically interesting. When we did the hole in the plate, that's when you were teaching each other. And all of this has to do with human interaction. But as we know, human interaction is subject to lots of strange patterns and rules that we only are barely now starting to understand. For example, the people around you are probably people you know or people from your own departments. If you go to you sat to a complete stranger. It's unlikely that you sit next to a complete stranger because we tend to sit next to the people we want. Students sit in the classroom typically next to their friends. But the best environment to learn is one in which there's a lot of diversity. And I found, with learning analytics, that often students form dysfunctional groups. Right? For example, here's a question, and because I have this seat map, I can ask the system to not just represent a bar chart, but also show me where the answers are before discussion, and again, where they are after discussion. And you can't see it very much here because most students got it correct, but the incorrect answers tend to cluster. So rather than having the students self-pair themselves, what we should really do is let the system manage the pairing. Why not have the system tell who the students should talk with? So using some kind of algorithm, we can pair the students, and then on the device it says, please discuss your response with this person on your left. You want to try that? Okay, so make sure you have entered your seat. So go back to where it says change my seat, and be sure that you indicate the right seat, because otherwise this is not going to work. And my apologies to the people online, because, we cannot easily pair you up. In fact, we cannot pair you up, period, not even easily, not even with difficulty. And I am going to ask you a question about probability. Okay? So is anybody needing help with selecting a seat? Okay? Everybody done with that? Okay. So, here, and I'm going to have, because we're not very densely populated here, and there are quite a few people who are sitting without a nearest neighbor, I'm going to have the system pair you in groups of 3, and I'm going to have them select people who might not even be immediately contiguous. So you may have to, look around to find the neighbor with whom you've paired. Okay, so here's the question. A meteorologist predicts and no talking. We're going to do this again in peer instruction mode, right? First you answer it individually, and then you talk to whom the system tells you to talk, and then vote again. A meteorologist predicts a 40% chance of rain in London and 70% chance in Chicago. That's a weird question. Doesn't it always rain in London? No, it doesn't matter. Which is the most likely outcome? It rains only in London. It rains only in Chicago. It rains in London and Chicago. 15! 10! Sorry. You are so engaged again, right? I mean, it shows how well this works. But time is running out. It shows how time flies when you're having fun. I was totally unaware of it. So please enter what you now, and I know I'm cutting you short, I'm sorry about that, but enter what you now believe to be the right answer. Initially, we had about 55% correct answer, which is right around the range that I want when I teach this way. Right now, we're doing substantially better, but we don't have all the answers in. I'm going to cut it off, though. We're at 77% correct answer. The right answer is it rains in London or Chicago. And, you know, I know you might be puzzling why that's true, but I don't have time to explain it. And I'm not here to teach you about probability, so I'm just going to barge ahead and wrap up my talk. Very quickly, what are we seeing when we actually pair the students? This is an average of about 10 students where we let the students pair themselves. These are students, the percentage who change their answer of the students who initially answer incorrect. You want those to change their answer. And the students who initially answer correct. You don't want them to change. So you want this bar to be as low as possible and that as high as possible. This is an average of about 10 random questions where the students pair themselves. Different algorithms, and we can significantly improve the quality of the interactions that are taking place in the classroom, simply because students do not tend to pair themselves optimally. Okay, I was going to show you a little bit about how we determine that algorithm and so on, but I don't have time, so let me wrap up. I want to show you some data out of MIT, the Effective Computing Lab, where they developed a little wrist sensor that measures electrodermal activity. And they show in that paper that the electrodermal activity correlates, can be used as a proxy for what you would measure with an EEG. You cannot distinguish between alpha, beta, delta, gamma, delta waves, but you can get an idea of the amount of brain activity that is taking place. Now, the great thing about it being a wrist sensor is that you can take a person and give him or her that wrist sensor, have the person go about whatever he or she does, and then download the data. It'd be really hard to do that with an EEG, right? Because it would look kind of nerdy if you had electrodes on your head and went around. Well, maybe at MIT students wouldn't mind, but I think normal people would. In this paper, they actually show something really interesting, namely that it's hard to pay utmost attention in a lecture for the reasons that I've already told you. Here are the data. It shows the brain activity for 7 days, day 1, day 2, day 3, and so on, all the way to 7. And you can see there are periods of intense brain activity and periods of much less brain activity. Starts at 4 o'clock in the afternoon when the person started wearing the sensor, and at 3 o'clock the next day. They also asked this person, this article, by the way, is not about education. It's really about the building of this sensor. I want to draw your attention to the parts. So they asked this person also to keep track of the activity he or she was involved in. That's in the small letters underneath the trace. You can probably not read it from there. But I want to draw your attention to parts of the trace labeled class. The trace goes flat. Compare that to the parts labeled sleep. I mean, we know that sleep is cognitively very important. There's REM sleep and so on. Information gets transferred from short-term to long-term memory. But this actually shows that your students are more asleep in lecture than they are in their own beds. Now, don't look at the screen. Look at me, because the answer is on the screen. Don't look at the screen. Look at me. There's one activity, and again, don't look at the screen, that matches class. What would that be? Watching TV. There it is. And this is something that we've known already for a long time. You put people in front of TV and they go into a meditative state. There's only alpha waves. Why? Because there's a continuous stream of information. There's no time to think. There might be emotions, but there is no cognitively very relevant process taking place. Now, if you stop to think about it, why would watching TV be different from sitting in a lecture? Same thing, continuous stream of information. You walk out of a lecture thinking you know it. Because basically you've had no time to be confronted with a misconception. Many of you thought you knew it about the atoms getting further away from each other, but you really hadn't had time to think through it all yet. So really, the lecture gives you a false sense of security. And in the end, it really is an illusion. So, in summary, education is not just about transferring information. It's not about getting students to do what we do. It's really much more than that. And I think learners really need to be actively engaged. Discovery, exploration is a must. Lastly, it's not the technology, but the pedagogy that matters. We could have done all of this without technology. Of course, technology does facilitate things, and I think this platform that I've demonstrated is particularly nice because it implements the pedagogy and it uses consumer devices. You don't have to have students buy clickers or anything. Furthermore, it avoids the pitfall of multiple choice assessment. And lastly, you can create a smart classroom anywhere. I can push not just questions, I can push slides too. Right now on your device, there's this slide. Look, it's on the screen on your device. I've pushed it to it, and I could push my entire presentation. We could go outside as long as there's some kind of a network. We can create a smart classroom anywhere. We're no longer dependent on the architecture or the infrastructure provided by the learning space. So I want to thank many people who have contributed to this research, and if you're interested in a copy of this slides, they're on my website, which is right there. The URL is right there on the screen. So thank you very much for your attention.
So I'm conscious of the fact that we've run slightly over time, so I'm going to restrict it to just a couple of questions in here, but I wanted to give the first word on questions to the online audience. And again, I know we've had some issues with bandwidth and exceeding the number of connections. So to the people who are still able to watch, that's great. The question that came in, it was about the process of peer instruction. And it was when students talk and discuss questions, they get the right answer. How do you convince them to answer alone on the first vote? So how do you stifle that conversation that might otherwise break out?
That's a very good question. My microphone works again. That's a very good question, and I do it exactly the same way I did here. I encourage, of course, I never get 100%. This is a very good question. If I were to wait for 100% of the students to answer, I'd be waiting forever. And typically, I cut you off here after 80% of the questions were answered. Now, that creates a problem if you give an incentive for answering the questions. And in fact, there are many instructors who give clicker points, either for participation or worse, for getting the answer correct. I would argue against both. First of all, if you give points for getting the answer right, then the students will do whatever is necessary to get those points, which might not necessarily be whatever is necessary to get it right. All of a sudden, the focus is on getting points, not learning. And the same, to some degree, is true when you give points for participation. I've made a hobby out of collecting tweets, and some of them might not be suitable for reading out loud, but I've collected tweets and I'm putting them in categories. One, reason for coming to class for the points. Cheating, looking up the answers, cheating, clicking for others. Let me read you first a few clickers and a few tweets. And what I do is I look for the word clicker and class. Here is a student by the name of Marshmallow. Dear Professor, you force us to come to class for clicker points, but no one pays attention after because the notes are online. Can I go home? Sitting in class, Rupsaks. Sitting in class, bored to tears. It's kind of sad that I'm only sitting here because I want clicker points. Or here, rated M for mature. I just come to class for clicker points. I walked out of my geology class as soon as we finished with clicker points. I'm so done with that class. Right? And so on. It goes on and on and on. Here, no clicker questions? Man, fuck this class today. I could be studying for my exam. Or this one, I came to class and this dude didn't even do a clicker question. Hashtag waste of time. So our professor tells us that he forgot his clicker stuff. So you mean to tell me I came to this class for no damn reason? Or here, for example, gonna be a pro clicker by the end of this class. One class, 3 iClickers. Let me show you, posted together with a picture. Here it is. So clearly, giving points as an incentive for students to participate is not a good idea. You want an intrinsic motivation, not an extrinsic motivation. Now, how do you get that intrinsic motivation? Because that's not at all obvious, right? One of the ways I do it is by showing the students that the questions in class have a value. So what I would typically do is very early in the term, maybe the 3rd week, I give an assessment, a midterm examination or anything else, where all of the questions resemble the questions I ask in class. After that midterm examination or assessment, students come to me and they say, can we do more questions in class? Because all of a sudden they see the value of these questions in class. So that's how I would recommend doing this.
Anyone who got nervous and wanted to see if their course acronym was up there, you can maybe ask Eric afterwards. If you don't use Twitter, he might have data on your course from your students. Okay, a couple of questions from people in here.
Yes.
Sometimes I find students will give me an answer which may be the right answer, but when I ask them to explain your reasoning, why did you take this answer, they're giving me the right answer but the wrong reasoning. How do you ensure that it means, so what do I do in that case? When they give me the answer but they're not really thinking through it?
So what happens when students give the right answer for the wrong reason? And as we all know, that happens certainly in a number of cases. And I think in education, what really matters is not the answer. It's the reasoning that leads to the answer. After all, in any real, authentic problem, the outcome usually is known. It's the process that is important. And that's why it's so sad that in the assessment that we use in higher education, we put the focus mostly on the answers and not on the reasoning. So I'm very happy you bring that up. If I had done a more accurate representation here of the way I do peer instruction, you would have noticed that I would have asked one of you to explain why the chance of it raining in London and Chicago is higher than that of raining just in Chicago. So I would have given the students, the audience, the people in the audience, an opportunity to articulate their thinking. And let's say that you have the right answer for the right reason, but I happen to have picked on somebody who has the right answer for the wrong reason. So that person articulated his reasoning and it's not correct. One way would be for me to say, that's wrong. Right, but then again, I'm just stepping into my authority and talking down to the students. A much better way is to do the same way people in business schools do who use the case study method and say, well, is there anybody else who wants to argue differently? And you would have then probably had your hand up already, eager to say, I chose the same answer, but not for that reason, but because. And then that other person would have gone, oh, yes. So, I mean, after all, this is still the beginning of learning, right? We're still at the beginning of the learning process, assimilating that information, building mental models. So that's how I would have done that.
Okay, time for one last question. Yeah, come on.
Someone earlier on referenced Paulo Freire. This is when the banking model, you got a little sort of flustered about that. What do you think, beyond the fact that you're here to pitch a particular product to us, what's the difference between your approach and his?
And who was this?
Paulo Freire.
I'm not familiar, so it's hard for me to describe. Are you?
He wrote a book called Pedagogy in the Press, which really goes over pretty much the material program. It's written in 1972, I think.
Wow. Well, I'd be very interested in about it. Of course, if you stop to think about it, the idea of the flipped class, which, you know, some people think started in 2006 and other people think it started with me, really started a long time before that. The first implementation of the flipped classroom is actually the case study method, which was developed at the law school at Harvard University right around the 1900s. And it's really interesting to look at this. So even before the book that you were mentioning, because right around the 1900s, Harvard was diversifying its students' body. Harvard used to attract mostly, you know, patrician families from New England, but around 1900, the president, who I think was President Eliot, pushed for a diversification of the student body. So all of a sudden there were students from Mississippi, from Canada, from California, from Mexico, and in the law school that posed a problem. Because all of a sudden the faculty in the law school realized we can no longer teach the law. Because the law had no meaning anymore, because the law in Mississippi is different from the law in New England, which is different from the law in Canada. So instead, they decided to teach the practice of the law. Rather than teaching the law, they teach the practice of the law. And rather than focusing on delivering the law to the students, they had the students read cases and interpret them in the context of whichever law was relevant to them. So students had to come to class prepared, having done the work that normally they would have gotten in a standard lecture on the law. And in the class, the faculty would basically pick on students, putting quite a bit of pressure on the students, say, you, what would you have done in this or that case? And how would you have argued? How do you differ from this person? I think the difference between the case study method and peer instruction is that in the case study method, which to my knowledge is the first implementation of the flipped class model, the process is serial in the sense that the instructor goes through one student after another. And in peer instruction, it's all students together in parallel at the same time. But I'm definitely interested in hearing more. So if you can send me that reference, that would be terrific.
It's a classic in education.
Okay. Okay.
Okay, I'm going to draw this to a close now, so can you join me in thanking Eric once again?
Do you know about that book? Do you know what he's referring to?